Hello, everybody. I wanted to show a different type of differential equation that isn't separable, but that if you use a clever substitution on, you can separate them. So it's a little bit of a sneaky technique. To be honest, I forgot about it from the time in between my college differential equations class to when I was teaching this class the first time. So it took a little bit of it's a trick you might not think of, is all I'm trying to say here. So let's look at an example. Let's say we've got a differential equation that looks like this. X dy dx equals x squared sine x plus y. If you look at this here, I hope you can see why this is not separable. If I tried to bring the y value over to the other side, I would either divide by y, but that would leave me with a y on this term, or I could subtract y, but then I'm not sure how I'm going to get rid of the x times dy dx either. Maybe I could try to divide by x, but then I have dy dx minus y over x, and that's not in the right form to integrate, so things aren't looking too good. So what I'm going to do is just start over. X dy over dx equals x squared sine of x plus y. And we're going to have an initial condition. I'll just write it up over here. We won't need it for a little while. The initial condition is that y of pi over 2 is equal to 1. Use that later. So the trick here is to recognize that you cannot write this in separable form, but you can get kind of close. If you divide everything by x, then what you get is x sine x plus y over x. And then what you do is you rewrite your differential equation in terms of a new variable. Your book uses the letter v. It's obviously arbitrary what letter you use. So I'm just going to say v equals y over x. And if I make that substitution, then I can also write that v times x is equal to y. And taking the derivative of that, I can write, and it's important to note that the letter v is thought of as a function of x. And this makes sense because y is a function of x, and x is obviously a function of itself, so you can define v as a function of x. And that's important when I take the derivative here. I'm taking the derivative with respect to x. So I have to use the product rule. So the derivative, I do f prime times g plus f times g prime. And then the derivative of y with respect to x is dy dx. So check out what I've got now. I've got a substitution. I can substitute my new letter v that just kind of came out of the blue. I can substitute that right there. And I can substitute all of this fun stuff for dy dx over there. So now I have dv dx times x plus v equals x sine of x plus v. And the beauty of this is that the v's are on both sides. You can actually subtract v from both sides. Boom, boom, cancel that out. And then you have dv dx is x sine x. And you made it into a separable equation. You don't even really need to separate it. You can just realize, oh, take the antiderivative here. But in our unit, what we do a lot is move the dx over here and then integrate on both sides to eliminate the differential piece. So now we've got v equals, well, x sine x is a product. So I'm going to do integration by parts. U equals x. I shouldn't use the letter v, so I'm just going to say dp instead of dv. dp is sine of x dx. du is dx. P is the antiderivative of sine, so negative cosine x. So u p minus the integral of p du, just like our normal integration by parts. So u p, I'm going to put the negative in front, minus the integral of p du. Double negative, antiderivative of cosine is sine. V equals x cosine x plus sine of x. I'm just seeing I made a mistake, actually. I made a small mistake. Does anyone? I hope you caught the mistake. I had this point right here, and I crossed out the v's, and then I wrote this down. Do you see what I messed up on? It's always exciting to see what I messed up on. I forgot that I had an x on the left side. So when I separated, I should have divided both sides by x, which actually just means I had to do the antiderivative of just sine of x. So forget this integration by parts garbage. It's actually a little easier than I thought. I mean, I could, if we had an extra x, we can still handle it. We're not afraid of integration by parts, but it's actually a little easier than that. Antiderivative of sine is just negative cosine. So we have v equals negative cosine x plus c. And then remembering that v was defined to be y over x. So y over x is negative cosine x plus c. Before I solve for y, I'm going to go back to my initial condition over here. Y of pi over 2 equals 1. So that means x is pi over 2 and y is 1. So 1 over pi over 2 is negative cosine of pi over 2 plus c. Cosine of pi over 2 is 0. Dividing by a fraction is multiplying by its reciprocal. So 2 over pi is c. I return to this step now, and I write my general solution. I'll just type it in so we can look at the actual graph here. Y equals x times negative cosine x plus c 2 over pi. And that's a pretty cool looking graph. And let's see, do we go through the point pi over 2 comma 1? Let's see, x equals pi over 2. Is it right at 1? So this looks to be the correct solution to our particular differential equation. So that's an example of what's called either a homogeneous or a homogeneous differential equation, depending on how you choose to pronounce that word. So please comment, ask questions if there's anything I can do. I'll pop up another example of this as well, because it's just a little bit of a weird technique. The way you know to use it is when you can't separate and you see a y over x in your differential equation.